Hello, welcome back to our organic chemistry lecture series. Today we'll be talking about the Michaels reaction. This is another example of doing some enolate chemistry where we can make an enolate and then react it with a carbonyl compound. Now, with our Michaels reaction that we're going to talk about today, we're actually going to use a different type of carbonyl. Here, we're going to use a carbonyl that has a double bond adjacent to it, right? This is going to be our alpha beta unsaturated carbonyl. Now, we're going to use this, we're going to make our enolate, that's going to then attack our alpha beta unsaturated carbonyl. So we have to decide though, when we take our nucleophile, where's our nucleophile going to attack? Where's it going to attack on this carbonyl? Where are we going to attack? Now normally, if I have two places I can attack actually on this molecule. So let's look at it. How do we know where it can attack? Well, let's go ahead and let's draw a resonance structure of it. So I can bring these electrons coming up like this, and we can get a structure like this. And by doing that, bringing electrons up to the oxygen, the positive charge is going to be on this carbon here. So we have a positive charge on this carbon. And that's not surprising. We've talked about that before. And we use that carbon, the carbonyl, multiple times as an electrophile that our nucleophile can attack. So that's one place. Let's draw another resonance structure of this one. But now this time we draw a resonance structure. Let's incorporate this pi bond here as well. So I'm just going to go ahead and move this pi bond here. Again, as I move the pi bond here, these electrons have to go up. And so we get our normal, what we saw before. But remember, this pi bond is going to move over. So we're going to generate that species there. And we still have a positive charge to worry about. Get that positive charge right there. So we can see while we draw a resonance structure, electrons can move up to the oxygen, can generate positive charge here. But this pi bond can also move over as well. And we get a positive charge at this carbon in addition. So really on this molecule here, our alpha beta unsaturated carbonyl, we actually have two places that are going to have a slightly positive charge to them, right? We're going to have a partial positive charge. Our two places are going to be at this carbon here, at our beta carbon. This is our beta. And then also here at this carbon as, and this carbon as well, it's going to be partially positive at that carbon as well, on the carbon and the carbonyl. So we have to decide though, as we generate our enolates or their nucleophiles, where are they going to attack? They're going to attack at this carbon, or they're going to attack at the beta carbon, right? So let's look at that. Let's go into that in a little more detail. So let's use a real example of this one. So this is our nucleophile. It could be any type of nucleophile. But now let's change nucleophile to something that we work with, right? Something real. So as we said, we have two places on our alpha beta unsaturated carbonyl that can be attacked with our nucleophile. So for our nucleophile, let's go ahead and use a Grignard. We already know Grignards are very reactive, right? Very, very strong nucleophile. Very strong nucleophile, can't get much stronger than that one. So let's go ahead and draw in our alpha beta unsaturated carbonyl. And if we draw an alpha beta unsaturated carbonyl, our Grignard is going to be a very strong nucleophile. It's going to attack, right? This is going to attack, it's going to attack so fast, it's actually going to attack that carbon there. And we've seen that all the time, right? We know that our Grignard reagent is going to attack that carbon of the carbonyl. Seen that millions of times. Get that addition there. This is a very, very strong nucleophile. It's going to attack our carbon, the carbonyl. And what's going to happen in the second step? So this is the first step. Second step is addition of water. This is going to pull off the proton. And we generate what? We get to that species right there. And so we can see from this is that our Grignard is going to attack, it's going to attack the carbon, the carbonyl, to generate this species with this alcohol here. Now, what we can say about our Grignard is that as it attacks, it's actually attacking via a 1,2 addition. Right? We've seen that similar before. We talked about 1,3-dienes, right? this idea that this is going to attack. This is carbon 1, and then that's position number 2, 1, 2 addition. So when we look at this molecule, what did we add to it? We added this carbon group at this carbon, the carbonyl, and we added this hydrogen here. So that's why we get that 1, 2 addition. So with our strong Grignard nucleophiles, these are going to be a 1, 2 addition attached to that carbon of the carbonyl. But for our Michaels reaction, we're going to see something a little different. And we're also going to need a nucleophile that's maybe not as reactive, maybe not a little bit less reactive. So we can see, instead of a 1, 2, let's look at a 1, 4 addition. So let's look at a 1, 4 addition. So that's our 1, 2 addition that we've seen all the time. So now let's go ahead and let's look at a 1, 4 addition. So let's draw in our carbonyl again. And this time now, we want something that's going to attack that beta carbon there. Because we know this is a partially positive and this is partially positive. We want to attack this carbon. So what we're going to use is we want something that's slightly less nucleophilic, as we saw for our Grignard. So we're going to use this species here. And we've seen this one already before, right? Where we've had this enolate. And we talked about this enolate between two different carbonyls. This enolate is actually it's nucleophilic, but it's not as nucleophilic as, say, our Grignard region. So this one here with this enolate here, this is going to be a good addition for our Michaels addition. Where our Michaels addition is going to be that 1, 4 addition. So if it's a 1, 4 addition, what are we going to attack? We're going to attack this carbon there. And what's going to happen? Electrons are going to move here, and electrons are going to go up there. So let's see what that looks like. And here, we're going to have our group bonded to it. And we get something like that. Now, what happens next? This is going to be our first step. Step 2 is what? Addition of our water. Now, remember, we talked about this already, right? As our water is going to be added here, this doesn't want to be, this oxygen doesn't want to get protonated because we don't want to make an enol, right? Enols aren't very as stable as, say, a carbonyl. We want that carbonyl to come back. And so what we can do is electrons can come back down. And this one can take this proton here. We get this species here with this hydrogen been added at that position there. And so from this reaction here, we have a 1, 4 addition. Now, we have one carbon 1 here. This is 1, 2, 3, and then 4. So they call it a 1, 4 addition because we added a group with the 1 carbon. And generally, you would have this oxygen would protonate this enol group here, right? To generate that enol form. But we know it would tautomerize and form the carbonyl, okay? So we don't generally see it in that enol form where this would be protonated. We generally get to see it in the carbonyl form. Because if we protonated that enol, it's going to tautomerize to give us back to the carbonyl. So what we're doing through this mechanism here is just showing that the electrons can come back down and we can pick up that proton, and then we've finished our mechanism. This is going to be our 1, 4 addition. This is going to be our Michaels reaction. Our Michaels reaction is going to be that 1, 4 addition. So the important thing about this is that we understand the mechanism, we understand our type of enolate that we're going to react it with. It has to be an enolate, not as reactive, right? We couldn't use one that's just a normal enolate like this. This wouldn't go by a 1, 4 addition. We need an enolate that's going to be somewhat stabilized, so it's not going to be as reactive. So let's look at some enolates that we could work with for our Michaels addition, Michaels reaction. So we saw these type of enolates. So this would be a great enolate to use for our Michaels addition. So this would be a 1, 4 addition. We also see enolates like this. Things that we saw before, right? We saw ones like this. This would also participate in the 1, 4 addition. All right, let's also do a 1, 4 addition. We could have two esters off of here as well. These ones would also participate in that 1,4 addition with our alpha beta unsaturated carbonyl to do our Michaels reaction. Notice what all these type of elates are. Right? They have two carbonyls attached to the same carbon. Remember, to make that elate is not as reactive. It's going to be more stabilized. It's got a lot more stabilized, so it's not as reactive. So we can do that 1,4 addition, where we're going to attack what? The beta of our alpha beta unsaturated carbonyl. That's going to be our Michaels reaction. In the next video, we'll do some more examples of Michael reactions, just to get more comfortable with doing that. Thanks.